Okay, let's stream some theorem proving. All right, in a previous video, I got started on this proof of the Schwartz-Zippel Lemma, which I think is right here. So now I'm going to try and continue that. Immediately, though, I'm faced with the problem that there's a lot of red. So let's try and figure out why that is. Can I restart the file? It's the issue that I have like the wrong very possible that I just have the wrong version of lean running because this is an old branch. Oh, maybe let's not delete that yet. Delete processing, it says. Okay. Let's take a look at what the the nightly version is. In toolchain 531. That seems pretty old. Okay, we should probably try to merge. What we should do is we should try and merge master. Try origin master. Version changed, great. And let's just happily sync all of that. So now this branch is synced. 620 is the new version. Cool. Let's restart Lean. See what happens. Let's go to the Schwartz-Zippel file. Let's see, is it possible to like adjust the sizes of the screens? Okay, it's weird, but I might have to like get the cache or something. Yeah, like if I pause, I do make execute cache get. Let's see what happens. Does not seem to be aware of what's going on. Okay, no, it's getting things. Gives me this warning like it always does. Not sure why. No files to download. Okay. Okay, well, that seemed to be successful. Okay, it's telling me something's wrong. What happens if I now like restart the server? Now that I pulled all those cache values. I seem to realize that the server was supposed to have restarted. Client is not running. Oop. Now I think thinking again. And it's compiling. Beauteous. All right, cool. So this is good. Now let's try and interpret where we were. So we were following the Wikipedia proof. Let's pull up the Wikipedia proof again. All right, this proof by induction on the number of variables in the polynomial. So the way that we were having to deal with that, as I recall, is that we needed to basically we're doing this for polynomials over fin n, and then for fin of successor n, we have some function that goes between like fin n and then option. We have like fin successor n and option fin n, and then we reduce that. Okay, so let me see more clearly what's going on. Okay, obviously this tactic was not needed. Induction n with 0 and a bunch of like tactic commands. Yeah, this is somewhat new syntax to me, but so this is the finished part, which is the base case. Relatively simple. And now we assume the theorem holds for all polynomials, right? Okay, so the first thing I do is I have p prime, which is, right, so I have polynomial p, which is a polynomial on the space of variables, which is of size successor of n. And what I want to do is I want to obtain p prime as described in this proof here, right? What is p prime, right? P to be a, yeah, like we have p, which is a polynomial in n, right? So like in this case, it would be successor of n. But we now assume the theorem holds for polynomials in n-1 variables. We can consider p to be a polynomial in x1 by writing it as a formal sum of coefficients times x1 to the I. Since p is not identically 0, there is some I such that pi is not identically 0. Right. Okay. So wait. Let's be clear about what p prime is here. P prime is a polynomial of multivariable polynomials. And so p prime, the coefficients of p prime are the pi's here. And that's what we have here, right? So I we define to be the Nat degree of p prime, right? So the largest, right? It asks for, there is some I such that pi is not identically 0. Take the largest such I, right? So I is the largest such I. And p sub I prime then is the coefficient of p prime for the monomial of degree I. And then it makes this declaration: the degree of pi is less than or equal to d minus I. And I think I've written something like that here, right? I've written it slightly differently. I've written that the total degree of pi plus I is less than the total degree of p. But that is an equivalent way of writing things without using natural subtraction, because I think all of these are naturals, right? Yeah. So if pi is not equal to 0, right? So the point is that we apply the inductive hypothesis to this, to p sub I prime. So I have h0 and I have h1, which I declare that the polynomial is not identically 0, which I guess is necessary to apply the inductive hypothesis, right? Because this is all predicated on the fact that the polynomials we're talking about are non-zero. Yeah. And this is, okay, so I replace IH, yeah. So this is my application of the inductive hypothesis here. The inductive hypothesis tells me that for all polynomials of fin n, right, just to like clarify, yeah, p sub I prime is a multivariable polynomial over fin n. So I can apply the inductive hypothesis to it. I apply the inductive hypothesis to p sub I prime. H1 is the necessary condition that says that it's non-zero. And S is this fin set, this finite set of values, finite subset of the field from which we are selecting our draws, our random draws independently and uniformly. Okay, so that works. That makes sense. Cool. So this gives me a new, like the new inductive hypothesis, which talks about which is a statement about, right? Basically, the statement that I have here is right. The statement is written in a slightly different way than I have here because right, equivalently, it's d times the size of s to the power n minus 1. But again, I don't want to use subtraction because that's hard to deal with in lean. And so I basically multiplied through both sides of this inequality by the cardinality of S. And so I have times finset.cardinality of S, and I have finset.cardinality of S raised to the power n here. And that's my inductive hypothesis. And so now I have to prove that that this, right, is less than, I basically have to prove the same statement, but for the successor of n. And this is where we probably get close to this calc block. Right. And so the inductive hypothesis tells me that this inductive hypothesis here is, I guess, essentially the analog to this probability statement. Sorry, like this one. And so now we have a sequence of, yeah, we basically have this calc block, which is expressed, all expressed in, unfortunately, all expressed in terms of probability. We would much prefer it to be expressed for clarity in terms of statements about the cardinality of various sets, but we'll try to work through that. So if the first thing I have is H2, what have I written? What is this H2 that I've written? I've written that the cardinality, when I filter, yeah, basically I filter this polynomial evaluation. I'm suddenly wondering if like doing things with fin n is gonna come back to bite me. Because if I do things with fin n, there's a question of like decidable equality, but maybe I'll just not worry about that. Anyway, so what is H2? cardinality, when I filter through this function here. So I have P, right? What is this saying? Like if I evaluate P with the variable assignment R, so I'm filtering certain variable assignments, right? I'm filtering like non-zero things, whereas here I'm filtering the zero things. That's somewhat interesting. Maybe I'll just like skip the interpretation of this a little bit. So what do I do in this whole sequence of rewrites? Let me like hide the info view for a moment. Right, the idea is so the thing I start out with, right, is like the probability, the sort of primary probability. And this is equal to the number, right, it's a small number, to D over the size of S. D over the size of S, interesting, yeah. So I filter polynomial evaluations where like for those like evaluations of the variables that yield 0 for the polynomial, I filter only those. I also have this function underscore finset, which is given a finite type in a finset, returns the finite set of all functions with range contained in that finset. Yeah, okay. This is a little annoying because I feel like there's probably some better way of expressing this. I might have even asked this on the forum before. There's like a better way of expressing this. And I think I got an answer which involved using something from the library that I didn't understand, unfortunately. Right, so this is the first thing we have. Right, this is the, it's just, right, everything is multiplied through by S. The annoying thing, I feel like everything is multiplied through by S, and it's also all been like added through by I, hopefully. Right, because to restore the induction hypothesis, put myself here. The thing that we're trying to prove is that if we filter by the things where it's equal to 0, and we multiply by S, and it's P times S to the next n. Yeah. It's sort of very interesting, right? Is it not right that I should immediately invoke POW of the successor and like cancel out this times finset card S? Can it possibly be that that's not the right decision? The thing is, I think I was going to do that, and then I decided that I actually needed the card S here to like invoke H2. Right, so basically what the first thing does here is it splits the filter into two different things, right? So like I'm filtering out only the things where the R evaluates to 0. And then I split it into things where R evaluates to 0 and it also evaluates to 0 for P sub I prime. And then on the other hand, filter where it's equal to 0 and where it's not equal to 0 for P sub I prime. Right? R composed with fin.suck is sort of casting it down to the smaller finite type. And so I am looking for, yeah, this is lean. Right, this is like the equivalent of B and B complement over here. So what do I do immediately after that? Right, so this is just this has to be some application of some library lemma. That seems sensible to me. And then, what do I do here? Right, so this is, okay, yeah, so what I do is I immediately like simplify this to this. I mean, is it the case that this and this are actually the exact same? Have I been kind to myself? Can I just like invoke, can I invoke like Conger or something? Or sorry. Okay, yeah, this is going to take a long time to load. But Patrick Masso's video showed that there's actually a way that I can make it not take so long. I think there's like this save tactic. Is that it? Like if I type in save. Does that make things go faster? Maybe the issue is that like all of the time is spent in like the later parts. Yeah, okay, whatever. But the Conger tactic, the Conger invocation works, right? Yeah. But does it work too well? Okay, wait, let's be careful. So I need to demonstrate, right, that, okay, like let's be careful. Let's do like Conger prime 1. I think this is how we like avoid going, okay, obviously it has no idea what I'm talking about. Is it just Conger 1? Congruence? Let's like more carefully, like we have finset card of all of this, right? We have like, okay, the second part of the sum is all the same, right? It's the sum of two different things. Am I mistaken? Right. Okay. No. Everything is multiplied by finset.card s. Yeah. So that's the first thing that we conger away, and then everything in this part of the sum should be exactly the same. And so it's simply a matter of showing that finset.card this is equivalent to like finset.card of this. I think it's actually like even further, like we can do finset card because the point is that A intersect B. Okay, let me see. Am I wrong about this? Is A intersect B equivalent to B? Let me like reconsider this proof here. Okay, 'cause, 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 ' the event, to denote by the event P of R1, R2, Rn equals 0 by A, the event Pi R2 through Rn equals 0 by B. So whenever A is 0, you randomly pick R2 through Rn from S. All right, Pi is this, like, this is what I call P sub I prime. This is this. See, the thing is, right, if P sub I right, it seems like these are like mutually like neither is, like, they could both be true, one could be true, the other could be true, neither could be true. Because, like, if I have A, right, if I have that this whole thing equals 0, then I could still have that Pi is non-zero. Something's a little... There are two inequalities. Okay, and there are two inequalities here. So if I apply, okay, if I apply Conger, like, let me just like carefully look at this. This is to say that, yeah, that this function equals this other function. So I mean, like, let's just like proceed with this proof assistant. Call extensionality with f. And I probably want to simplify. See if like the simplification recognizes that this is some like implication. Yeah. Ooh. Okay. Wait. I've simplified too much. What is simplify doing? I just wanted like the logical simplification. I think all I want is the and if and only f right, if and only f imp. Let's just do that. Yeah, simple like that. Show HF. Somehow I've generated two goals. I don't understand how that happened. Right, like, so the critical question that I'm trying to figure out is in this like first inequality here, is it that both, like, obviously the point is that probability A given B is less than or equal to probability B, and probability B complement, probability A given B complement is less than or equal to probability of A given B complement. But I don't know if one of these is like actually an equality and therefore perhaps easier to prove as an equality. Like, the question is like probability, right? Obviously, like, the probability of B and the probability of B complement, neither of those are guaranteed to be 1 or 0. And so if it were true that like this was an inequality, it would have to be the conditional. Okay, maybe I'm just like being dumb. The probability of B and the probability of A given B, right? Like this is just like a probability law, right? This is true from the fact that like probability of A given B is less than or equal to 1. And similarly, probability of B complement is less than or equal to 1. But how do so the issues that I'm not talking about probabilities, I'm talking about like cardinalities of sets. Right, so this is like this is the first block. Maybe I should like write out my calc block. This is like what corresponds to the probability of A. This is what corresponds to probability of A and B plus probability of A and B complement. Then this, I can get it to not do that, is what's supposed to be let me just like inspect this. Like this is A and B where they're both 0, and this is A and B complement where 1 is not equal to 0. And so what we have here is I have not changed the second part at all. And I've simply reduced this to B. Yeah. But the question is, like, was it permissible for me to do this? Is A given B equal to 1? Like, the question is, do I have to write, like, this? Or, wait, so no. I think that maybe the like point is that I need to skip this like second row here and goes like straight from here to here because I have probability of A given B, like A and B less than or equal to probability of B, like should not be too hard. And then probability of A and BC less than probability of A given BC. Which is like an interesting thing to express, but this like it feels like going from here to here is where this like 2 cardinalities of S is going to creep in. Okay, let's just like see what this is, right? All I've done here is to like, this is all exactly the same, but it's probability of B. Yeah, so like I have gone from like this to this. And so, I mean, there's no like harm in this, right? Does Conger like fail to work with inequalities is the thing? Yeah. Yeah, that's the thing is that like Congra now fails to work with inequalities. And so I might try like simplifying or something. Like at the very least, the simplification can get rid of like did the Congra even do anything there? It's strange to me that it seems like it did nothing, and yet it wasn't. Um, the first thing I want to do is strift on, is remove the I'm deeply confused. So this is something times finset.card s, and this is something times finset.card s. What I would like to do is like mol. Like this would be my like attempt to magically guess what the lemma is. Okay, and there is such a lemma. But it's it needs to be a rewrite using mol right. Okay, let's see if that works. This is unfortunate. I can't invoke this without the condition that A is positive, but that's also unnecessary. So, like, what I want is the version of this lemma, which is like the single direction, which, so it does have to be an apply. It's complaining. Like, is this the right? It is. Okay, this is time to go to the docs. Like, mol right. But this is an equivalence. That's not what I want. So, less than or equal to of mol of us, right? Why is this even like a condition to this theorem? If A is equal to 0, surely. Okay, wait, no, I'm wrong. Yeah, I don't really understand what's going on. Maybe it is like a necessary condition. Like, let's undo. Yeah, in order to like be able to reduce B times A less than or equal to C times A to the equivalent B is less than or equal to C. I swear this was just working, and now it's giving me an error. Maybe it has to be without the asterisk. Okay, yeah. Not the asterisk, but the prime. Okay, we've spalled off this additional lemma, but who cares? We can, like, if the fid-set cardinality of S is in fact equal to 0, then like this whole thing should be like trivial, and so we can just like put another condition in later. So like further, like moving forward, we have this and this, like, so I think this is like, we write like add cancel, right? It's like cancel or something. Much better to try and look it up here. It should be something like add cancel, add left cancel. Or le add right cancel. Maybe like add le cancel. And just make sure this is the same. So card filter p equals 0, not equal to 0, function of inset this. Inset filter. Yeah, I mean, will the simplifier find it? You could also try like apply question mark. Wait, I think I got rid of it. Addly add if right. Okay, let's just try that first. And now we can get a better view of what like simp tells us to do next. Okay, so that works, and it eliminates that addition. Okay, now there should be like a lemma that says that if I like the cardinality, like it should be like a monotonicity. Like, isn't there like a mono tactic? What if I just do mono, right? Like the whole point is that it's like card is the less than or equal to card. Okay, it has no idea what I'm talking about. There's like cardinality is less than the other cardinality can be inferred from like subset. It's like so like let's try like rewrite. Now this would be like an apply. This would be like apply inset dot card the card of subset. Let me like see cardly card. Cardly card of subset. Really? If I have two fin sets, like, okay, like finset subset card maybe. I can't even like interpret what this said, what this like subset. I'm just so curious to see what this lemma is. Subset if and only if equal of card LE. Okay. Card LT card. Okay, is it like card LE card? This is like strict subset, right? I bet it's just like card LE card. Finset card LE. Like, can I get finset card LE card? Finset.card LE card? Is it not, the goal is that I'm trying to prove that the card is less than or equal to the card. Okay, but is there a lemma that allows me to not deal with like this injection and just talk about being a subset? Card LE of subset. Okay, well, like everything else in the library is card LE card, so I don't know why it's this, but card LE of subset. Okay, yeah, so I have two cards. Does this simplify things? No, it seems to make them more complicated. I don't know why, but okay, the next step is like these are two filters of the same set. And the point is that one is a more restrictive filter. So apply inset dot filter. Like, okay, again, I'll go here like filter subset inset dot filter subset filter. Okay, this is what I want. Finset.monotone filter right. See if that works. So now I can do xdef. And then simplify. Wait, it's telling me applies to equations. Okay, the point is that I just want to like work off the definition. I want to like apply the definition of like, this is like LE for props, right? Okay, what are you applying? I don't want you to apply those things though. Just like, don't apply any of these. It's very interesting to me that it's not, I don't really understand. This is where I would like to unfold like the meaning of LE. Like this is like This is the less than or equal to relation, obviously, but like monotone filter. What could the name of this like be? Like surely like is it that like these are like functions? Is it that it inherits the less than or equal to relation from like pointwise function? It's a function type and it inherits pointwise the relation. So like apply like function.le. Like this maybe. Or rewrite. I mean, obviously this would be a rewrite. Function LE. I mean, it's the sort of thing that should be dealt with by the simplifier. I mean, it's like, yeah, pretty clear, right? It's just so this is pretty annoying. Okay, let's use like our library search skills. Okay, maybe like in fact maybe maybe that would solve it. If this doesn't solve it, we could, like our other option is to like please suggest things. Yeah, like maybe suggest here. It's like I would like to unfold the definition. Exact. Could not, yeah, let's try apply. Fine. Pi.ledef. Okay, this looks promising to me. Like pi, because it's a pi type, not a function type, but a pi type. Yeah, pi.ledef. In fact, I might just try like rewrite pi.ledef. Yeah, confusing because it's for pi types, not for other things. Okay, cool. Intro I. Knock things over. It's like tidy. It's like ASOP is supposed to do what tidy does, right? Is ASOP a tactic that exists? Is literally like A and B implies. Okay, cool. That cleared it. Sick. let's ask ASOP what it did. And let's also like delete all this other stuff. Try this. Rename a bunch of instances. I don't see the point, but whatever. Maybe if I do this, it'll be much faster in the future. Okay, and this final story is just to deal with this like random condition about the cardinality of S being positive, which we can easily introduce if we need to. Because if it's not positive, then right. I mean, if it's equal to 0, this is just obviously true. So obviously, like, this is not really necessary. Is there like a yeah, I don't know. Okay, I'm not going to deal with it right now. Okay, like this is the next calc block entry. And what have we done here? Let's return to the proof. So I think that like this is like probability B plus probability A and B complement. And so what I think we've done here is we've gone to, what have we gone to here? Right. Not familiar with functional programming. What are you making here? So this is lean. What I'm writing is a proof of the Schwartz-Zippel Lemma using this proof assistant software. Okay, so let's just like go here. Like see what the goal state is. I'm a grad student at the University of Illinois. It says there are no goals. How can there be no goals? Did I delete the sorry arguments? Let's delete the question mark from the A sub. And so my intuition tells me that like we want to apply the same technique here. Except here we're probably going to want to do like add if and only if left. This is going to be my hello. Okay, unknown meta variable. I have no idea what this error message means. It's giving me that. Is there a meta variable? Oh, is this because so maybe like the meta variable is referring to is this, which would be unfortunate. Because to me it is pretty obvious what that meta variable is. Proof writing is miserable, but someone has to do it. Yes, very true. Okay, wait. I'm a little confused because now it seems to be telling me that it does understand what I'm saying, right? There's an equal sign here. Oh, but I also feel like this probably should not be an equal sign. It should probably be like a LE. So this programming language is the lean theorem prover. Now my calc tactic is failing. Has type this, but is expected to have a completely different type. Oh, does this have to do with the fact that like my last thing here is not like d minus I plus I equals d? Yeah, I need to remember everything is multiplied through by cardinality of s to the power of like n or successor of n or something like that. Okay, that's okay for now though. Actually, maybe it is something that I want to fix now because it's going to continue, like the calc block is going to continue to give me this error message until I fix it. It's going to be, right, if I don't fix it, then it's going to be strange. Like, so what am I trying to prove with the calc block anyway, right? Like, what I'm trying to prove is that, okay, so this whole big thing, in fact, like, can I not simply, so I'm trying to prove, okay, wait, what happened? What am I looking at here? For all p not equal to 0 implies that this is less than or this. It does not. I wonder if like the save tactic is throwing things off. Let me delete that. Some weird bug. So I should have the inductive hypothesis. Yeah, so I have inductive hypothesis, I have H2, and now I'm just trying to prove this. And the calc block, yeah, should not be complaining because it's FinSet card, this times that. Right. In fact, like in principle, I can like delete this entire block and replace it with an underscore because it will infer that, but just for clarity's sake, it'd be easier to leave it. And the last thing here is the thing that it's supposed to be, right? Total degree P, card S to N, total degree P, S to N, yeah. Okay, but it's telling me that mol, right, is not correct here. Which is surprising because it seems to me that that is exactly the structure of what we have. Oh, I see. This is interesting. What have I done here? I have apparently written, like, so this is what I have here, right? It's all times finset.cardS. And what I've done here is that I have finset.cardS and finset.cardS. Okay, wait, is maybe I was mistaken in thinking that I like needed to do this. Maybe all that I've done here is apply distributivity. So like if I do this and I do like that would be like rewrite add mul and don't do anything else and say that I'm done. what happens? Well, it's not exactly complaining. And then I have to delete the sorry, of course. It's complaining of an unknown metavariable. Okay, I'm not going to save here either because I'm worried that it's throwing my stuff off. Okay, it shouldn't be necessary to prove this like positive thinset.card_s. Mul. Let me go back to the documentation. Mul. Except that it's mul. So the tactic, or the lemma I invoked is mul, right? Perhaps it's this? No? Maybe it's only for natural numbers, right? It's only for types which are always positive. So maybe like nat.mul. Nat.mul, right? Okay, this looks more promising. And I'm going to apply it, and I don't think I need these square brackets. And I hope that this will be good. Yeah, and it's complaining about the sorry because no goals are to be solved. Wonderful. Okay. What I thought I was doing here was rewriting add_mul. Like so before, and I just did this. Yeah, so this was actually much simpler than I thought it was. Okay, cool. So this is the next part of the calc block. Right, so I simply invoked I invoked the distributive law. And now I'm returning over here. Because what I think is about to happen, okay, yet another equals though. So it's always surprising how it's not a less than sign. So I invoked that, and now what do I do? So what I'm saying now is like thinset.card, thinset.filter this, right? This should be the same as like this, right? I assume. Like if yeah, they're the same. And then I invoke the inductive hypothesis. Okay, wait, no, that's not quite yet that I invoke the inductive hypothesis. That comes in the next calc block, which I should describe. But what am I doing here? So I thinset.card, right? Those two are equal. And for the second half of the sum, So the finset.cardS goes away. Yeah, it looks like this is where I should apply the inductive hypothesis. But it's strange because obviously, apparently I thought I was applying it here, but it looks like I should be applying it here. I mean, what am I doing exactly? Let's invoke Conger. What is I? I is the degree of P prime, right? It's the highest, right? It's the highest I, the largest such I, right? The largest such I that Pi is a non-zero. So what I want to prove here is that what exactly has happened? Finset.card, finset.filter, where evaluation of P equals 0 and the evaluation of Pi prime is not equal to 0 times the cardinality of S. I'm saying that this is equal to I times the cardinality. Finset.filter Pi prime is not equal to 0 only, without any reference to P at all. Okay, so right, BC. So I think what I've done here is like this, right? I've done this. Yeah, this is simply distributed, and then I do something. Right, the inductive. I only use the inductive hypothesis in the very last step. I can reverse engineer exactly like what's going on. So like I have that dot second. So everything I think is multiplied by like finset.card to the power n plus 2, which is of course pretty weird, but this is what I think I said. Yeah, I needed to like rewrite LHS to have this. Right, so I did Conger. Probability of B complement. Right, I think it's wrong. Okay. I mean, I think it's like, again, I think it's wrong to have the equal sign here. I think it's going to have to end up being less than or equal to. And then it's going to be, going to need this one. Instead of the Conger application, it's going to have to be like left. Okay, it seems to have not been too upset by that. Okay, so let's try and like interpret what's going on here. We have the result of filtering out filtering out the 0 and filtering only p equals 0 and pi is non-zero. And we claim that this is basically, if we like divide both sides through by s, I mean, like, the right hand side of h2 is actually like exactly equal to the right hand side of my goal, which strongly implies to me that I should be using transitivity. Right. I guess that like the point is that the next step less than or equal to is it's just like rewriting this. Apply. Less than or equal to transitive. Okay, it's complaining. It's telling me I did something wrong. Wait, what is H2? Oh, H2, not HI. Okay, or not IH. I'm getting confused. So like this, like what must have happened is like the last time I was coding this, which was like a month or so ago, I must have like realized I needed this lemma H2 and decided to extract it. So I needed to apply that. Okay, so this is cool. Now we have to figure out what H2 even is. But before we do that, like this seems sensible. Let's do this. Is this going to be easy to prove? Filter p equals 0 and pi is not equal to 0 is less than p is not equal to 0 and pi is not equal to 0. That doesn't look right. Something about that looks very wrong. Like I have no guarantee. I have no guarantee that that's true, right? I wonder if H2 is not correct. What is this H2 and why did I think it was correct? H2 is like, basically what I'm trying to do is I'm trying to rewrite A probability of A and B complement is less than or equal to probability of A given B complement. Which is less than, which is itself by the inductive hypothesis less than or equal to I over S. The thing is, there's no like I. There's no reference to I in any of like the first three lines of the inequality. So it seems like it can only be introduced via the induction hypothesis. Right, P sub I prime is the only place where I is really referenced. Yeah, so we have to like extract that. Like, what is the thing that we have that at the end of the day was equal to like A and A like and BC. Right, so we had like okay, yeah, like so this is where we like we realized that the alterations to the theorem that we've made to try and make it more amenable to like code are throwing us off. So this is like okay, so what do we have? What do we need to prove? Let's like okay, let's like delete H2. In fact, like, so we have this, right? We have then this. So at the end of the day, we have degree of P times S to the power of the successor of N, which is like a factor of difference, right? So like D is the total degree of P, right? And the factor of difference is like N plus 2 factors of the cardinality of S. And so if we like go back to here, right? Like probability of B. The point is that if we're multiplying, if this is supposed to have like a power of finsat card S to the power nat dot sec n, because well then this should also have that, right? The like D minus I over S. And so the point is that like here, when we introduce the probability B, like so we have here, we get to the probability of B. Which we prove here, which is finsat.card, finsat.filter, all of this. Point is that this should be like D minus I, it should be at least D minus I over S. Or no, to be more precise, this should be at least D minus I to the power, D minus I times size of S to the power N plus 1. Man, that's like stupidly complicated. So like after I apply the distributivity, it's even simpler, right? Because this is all that I have. There's a factor of this. And so maybe I should just use the natural subtraction here because it's like blowing my mind. But what we should have is that this this quantity here let's just like make another half H3. It seems like this quantity actually is supposed to be less than or equal to the quantity d minus I times, right, and I said it was like a power of 2. And set dot card s raised to the power, I think, just n. And it has no idea what I mean by d, of course. But d, what is d? It's the total degree of the polynomial. It's n, right? Wait, what? Okay. D is the total degree of the polynomial. So it's like p dot total degree. I is p prime's nat degree, and d is the total degree. Okay. Yeah, here it is. This is the quantity which we call d. Okay, so sorry about that. But this should be something that we need. Maybe I'll call like this like h. H first half, and then I like also want to do h second half. Yeah, like hopefully I can like finish the calc block and just like extract the lemmas I need to the calc block. Okay. So h first half is this. Then the other part is h second half, right? So this is h first half. Just trying to boil it down. Yeah, like I don't even necessarily what's going on here. I think I'm gonna like try commenting out like h2. And like this whole thing, I want to like comment this out as well and just try and approach it from the end. All right, so I have those two things. Yeah, very frustrating to have to use natural subtraction. Right, of course, it's a valid subtraction. Looks like none of this is right. Like total degree pi. This is not right, right? Like total degree pi. Do we ever make reference to that? We make reference to the degree. I guess we do. Degree. The degree of pi is less than or equal to d minus I. That's this. But in my first half thing here, I refer to it as this. I wonder if you can do like have calc, right? Like have underscore by calc. That would be a weird syntax. Yeah, maybe like the easiest way is to just do the whole thing in two halves. Like, let me like forget about all of this, right? And simplify things. I think it's okay that yeah. Okay, so I have like this statement. All I do here is this. And what I want to say is that this I'm going to call this the second half. This is just going to be, what's the label of this? Just I. Yeah, natural subtraction. Sorry. All right, the point is that this is like a valid natural subtraction. Actually, just gonna like comment literally all of that out. Go straight to the end. And so like, how am I going to prove this? I'm gonna point is that I'm going to apply the two lemmas I just defined. Why is that even necessary? It's so hard for me to like understand. Let's comment this out too. Let's just like just gonna do like rewrite add.o suck then we do like a add.moling all right. We gotta do molcom. Rewrite molcom. I think it has to be backwards. Something's not right. Is that card S? Oh. Did that no, Molosok is what I want. I don't know the names of fundamental arithmetic properties. Molosok. Yes. The point is that this gets rewritten into something. I always feel like I get trapped in this, like when I do a calc block, I always like constantly doing the same like moly mole right applications every time. And I feel like there must be a more elegant way of doing it. Okay. Let's just try it like let's just try this. I'm gonna do the whole thing again. Just for visual. We have this here. And we have this here. Question is add the right. Okay. What do I have here? I have a sum. I have a sum. would like to prove that. Rewrite failed. Quality or, okay, I want to apply. Not rewrite. Okay, and the good folks are telling me that this is what I need to do. I'm indeed right. Second, everything else could be deleted or commented out, I guess. No, like I already did it up there, so that's fine. Seems fine to me. No. Like returning. It seems like I need to like do the distribution thing. What was the name of that lemma? It's like add mul, right? Rewrite add mul. I think this is right. And now this is where like this is like natural subtraction comes in, but like add t sub. It's bad that it's not called t sub add. This is where like apply should in theory like find the exact right one. I mean, so really it should be like le.ruffle, right? Yeah, le.ruffle. But what I'm looking for is like a minus b plus b. Le of eq. That seems a bit more correct. Now please suggest. This looks right. Can I just like sub add cancel? Sub add cancel. Yeah. And that does the add cancel, right? This is apply net sub cancel. Net sub add cancel. Right. And now I simply have to like prove the last fact, which is that I, which I know to be the degree, the natural degree of like p prime, is less than the total degree of p, which makes sense because the total degree of p, right, like the degree of p prime should be like a component. So I'll leave that side. And now I'm mostly done. Okay, I'm going to take a quick break. Right, so the microphone's still working? Yeah, I think it is. Okay. Let's quickly double check that the each first half and each second half lemmas are concordant with what we see in the proof, right? So like I have s to the n here. Right? Everything's an integer, so I feel like I haven't lost anything due to like weird natural subtraction issues or natural division, rounding. Everything's being multiplied, so that should be fine. I have the set of R values which lead to fin n. Right. So this is the right. So this is a space of s to the n different possible different s to the n plus 1 different possible assignments to the values x1 through xn plus 1. And the probability, right, the event of B, right, the probability of B is the event where P sub I prime equals 0. And what this first half lemma is asserting is that that probability is less than or equal to t minus I, like, right, so yeah, so if I were to like divide through by s to the n plus 1, it would be over s. So that looks right. Similarly, we have an r here, which is ranging over s to the n plus 1 different values. And similarly, if I divide through by s to the n plus 1, I get I over s. So I think that's correct. So I think both of those lemmas are going to end up being provable. Just like double check that everything here is provable. Right, like I think this is provable. It's one of those things that's going to be like tricky. Oh no, I've actually even gotten rid of the natural subtraction. So now I simply need to prove that, yeah. In fact, this is like a good math live lemma, for example, right? This is simply like if I have a multivariable polynomial, right? If I define p prime as like the Finn-Suckequiv multivariable polynomial map, then its total degree should be less. Like I'm gonna like notate like to do and of course I'm developing this in MATLAB, but I should just say that this should be a lemma, right? Right, it's true whenever you apply Finn-Suckequiv, multivariable polynomial.Finn-Suckequiv. Finn-Suckequiv. There are a few more sorries here. Let's like what are these like early sorries? Are these like actually easy sorries or are they not? Right, this is okay, so this is where I do like the FinSet, yes, FinSet card, okay, yeah. So I'm gonna need to do this sort of same like mechanics here. Right, as always, apply this. Crazy. Oh, so wait, this is just an equality, so I can actually do a conversion. Yeah, so the cardinality of this is equal to the cardinality of this plus the. So I feel like there should be some lemma about like if I take the cardinality of a disjoint union is equal to the cardinality of like a, except that I have no idea how to find that. Maybe like principle of inclusion exclusion. Like it'll be like inset card Cap, card cap. Card add card. Maybe card add card? Card union, add card enter. Yeah, interesting. It's almost like I would expect this theorem to like be written the other way. Wait, what's the difference between this and this? Card, oh, it's the order in which a card in. Okay, that doesn't concern me. So let's just rewrite that, yeah. So I have card plus card. Rewrite backwards fin set dot card union add card enter. Okay. This is where I would benefit to like know the like syntax of being able to say that the second thing here is like the point is that this is 0 and this is equal to this, right? This is equal to this and this is 0. Can I do like rewrite filter union filter? Seems possible. That exists. Filter union filter. Right. Okay. What I'm looking for is that like the filter of like X on P and the filter union with the filter on Y on P is equal to the filter of X or Y on P. Filter union filter. What? Card union and a card enter. Data fin set. Maybe just filter union? This is why it's super annoying. This is it, isn't it? It's it, filter union. No, no, this is not what I want. This is what I want. Filter union right. I guess it's right because like of the two arguments to filter, it's like doing something on the right one. This is sort of weird. I mean, it's in a way it's sort of weird because like to filter a set, it's just to like conjunct that set with another set, right? Because a set is in fact defined as a proposition. And here we have like fin sets, but okay, so filter union right. That worked. Filter intersection right. Something that I also want to do. Inter without the section. Still complaining? Inter. Filter union. Filter union right. Filter inter distrib. Okay. Okay, so for one thing, this is pretty, this is like hilarious because we have like filter union, and the analogous thing for inter is should be filter inter, but it's not written that way, right? It's like this is these two lemmas are analogous, but their names are not analogous. And furthermore, filter union right should have an analogous lemma, but it does not seem to have that. Filter or. It has the analogous lemma, but it's just down here and it's written differently. Um, and then there's filter and, which I believe decidable pred. Like filter and. Okay. So like there's got to be like this has got to be like some weird math lab thing because filter and so filter and here and then filter union right. There's okay, we have filter or and we have filter union right, which are like they're just the reverse of each other, right? Filter union right and filter or. Filter it's just the like symmetry of equality, right? So surely if I go to the like source, this is what aliases are for, right? Filter or filter union right. And I think they have the exact same conditions. Okay, like to do note filter or is a sim of this golf the proof. And then the other problem is that filter and, right? So filter and is what I need. Maybe so should filter inter right. Okay. But okay, so returning to like what we were doing, we decided that it was filter and, right? now I simplify. And the entire rest of the problem is magically solved. Odds on will simp succeed. That's unfortunate. It seems that it did not succeed. Man, I thought it might work. Right, let's just like clarify what we have in here. We have like, okay, okay. I am looking, like when I mouse over it, it completely whites out the thing that I'm trying to look at, which is not a good feature. This must be like an issue with like the color scheme. If I change my color scheme, let's try that. File, code, settings, theme, color theme. Let's do like a light theme, light plus. Yeah, it's totally fine with a light theme. Let's like select a nice dark modern. Maybe this would be good. Okay, yeah, this is a nice theme. We can move forward with this theme. P equals 0, and this P sub I prime equals 0. Or P equals 0, and P sub I prime is not equal to 0. Like, not E. Can I like... So I should like simplify that. The thing is, like, can Aesop solve it? Like, in theory, Aesop might. I feel like if Simp didn't solve it, Aesop probably won't, though. Maybe the like decision now is to, yeah, Aesop failed to solve. Tell me what you failed. Failed to prove the goal after exhaustive search. Okay, delete that. Aren't there like, okay, what I need to be doing, like there's like the De Morgan laws, right? Like these are just applications of the De Morgan laws. Yes, yes. De Morgan. Okay, but or and so this is like and or right, I think. Simp right and or right. Except I want it in the reverse direction. Now is there like and, right? Hmm. Did this work? Apparently not, because it exploded. What the heck? Polynomial.coef? What? See, this is the annoying thing, right? It's like simple logical, like in here, I have something that like is this like simple logical formula that obviously reduces, and yet it's very hard to like figure out how to reduce it. Have I got this right? My there's an or there should be an or in the middle. What? Okay, obviously I've got this wrong. I think I need to be doing something on the left. Is there more above? Okay, yeah, I got this. I'm something's wrong. Let me like carefully look. This is of the form A and B or A and C. A and B. A and B or A and C. This is and or left. A and B or A and C. So this needs to be and or left, and it does need to be in the reverse direction. Okay, let's see how this does. Of course, I don't know why it's like exploding, like, yeah. See, still, it does not conceive of how to like simplify this. It's like multinomial x composed from the suck, polynomial.coef, right? This is just a statement or this negation. Is it like, does it not know the law of exclude middle? Is that the problem? It's like not or. Like P or not. Like this is like the law of the excluded middle that it doesn't want to apply because it's classical or something. or not. Yeah, interesting. P or not P. Do we have or not true? Or not if true? Or not eq true? Eq or maybe eq or ni? Eq, it's either equal or it's not equal. So like, here's my other question. Did like this manage to simplify this other thing or did it not? I think it did not, right? Yeah. I feel like there should be like A and B or A and not B, right? Like that's the like structure I have here. A and B or A and not B, if and only if. Let me do a library search that lemma. Lemma blah 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 EQ prop P. Let me just get this right. P and Q. Okay, wait, let me like definitely get it right. Ugh, it's gonna reload. P and Q or P and not Q, even only if P I back to something. Failed to find it. Can I like use some classical reasoning or what? It could not close the like classical. I'm also worried that like maybe this is what's getting it down. So just that's apply, right? Is there literally anything I can apply here? Like, okay, what would I expect this lemma to be called? I would expect it to be called like and or and not if. Sorry. And the other one is and them. Like, yeah, like what if I simplify with these like two lemmas I just made? Yeah, okay. Radically simplified. And that's equal to that, and so all that remains is to show, okay, wait, did I do something wrong here? Wait, P and Q, or P and not, okay, I'm literally saying the wrong thing. P and Q and P and not Q is like false. And that is what we should have. Cannot be the case that Q and not Q are the same. I mean, obviously P is like not right, but this should like simplify to that, and that should simplify to nothing. Okay, I think I've like finished this now. So that's all the stories in the calc block, except for this last one. Sure. That's 0. Yeah, great. Okay, so that finishes the calc block. It's almost like the entire thing which is done. And so now I just have to like prove this first half part and the second half part. Let's like consult again. First half is saying that, right, by hypothesis, this is just B, right? Yeah, I got rid of the like A given B, so it's just that B, probability of B. Right, so I think the first half does not use the induction hypothesis, right? It's like, it's a little, okay. No, okay, I'm confused. This is the logic behind the first half statement. And it does apparently use the induction hypothesis. Whereas this is the logic behind the second half, and it does not use the induction hypothesis. But it's also a little complicated in that it's like A intersect BC. If PI is not equal to 0, then Px1 through R1 is of degree I, and thus not exactly 0, so the probability that P equals 0 given is at most I over S. I thought that there was some tactic that like solved like Tato, right? Tau. Okay. Well, that was fun. to the Lean 3 version of this tactic by default attempted to avoid classical reasoning where possible. Lean 4 makes no such attempt. iTauto is designed for that purpose. Right, so this is like iTauto would not succeed. Yeah. Oh, wait, what? It just doesn't know the tactic. Okay, maybe it's not implemented or something. iTauto is designed for that purpose. Okay, whatever. It's fine. It doesn't really matter to me. Yeah, that's a good note. Again. Yeah, returning to the sorry for the first half here, which apparently uses the induction hypothesis. By the induction hypothesis. Right. So, right, the total degree. D is the total degree. So, right, the degree of pi, which is this like n minus 1 variable polynomial, is less than or equal to d minus I. Because, of course, like if it were the case that like pi had, okay, wait, let me think about this a little bit. Yeah. So if in fact the degree of pi were like greater than d minus I, then the degree of p, right, would have then p would have a term of a form x1 to the I times pi like this other of degree like d minus I. So that term, right, that x1 term would have total degree greater than d, which would be a contradiction. So maybe I should make a lemma for that. It's like apply the induction hypothesis. Let me get a sense of like how am I going to apply the induction hypothesis? Yeah, it looks like I'm very close to applying it, right? I mean, basically all that I have to do is like observe that the total degree pi is less than or equal to d minus I. Yeah, natural subtraction. It's interesting that it's like the advice of Kevin Buzzard is to always avoid it. But I'm not like quite seeing right now how to do that. I guess it's just because it's easier because this entire proof here is written in terms of natural subtraction. And maybe if I thought about it more, I would be able to remove it. Right, so the key thing is to prove that the total degree of p sub I prime is less than total degree of p minus I. And I guess the other thing is to prove that finset.card p. Yeah, I get the sense that the left-hand side of the induction hypothesis and the left-hand side of the goal are in fact equal. Function, the finset, function finset. It's this function finset thing that I've defined. It's a little bit annoying because I get the sense that I feel like I was told at some point like what I should use for that, but I feel like I don't, like it was some weird like dependently typed version. And I feel like I didn't want something that complicated. I wanted something I could read without knowing about dependent types as much. like a dependent function. Yeah. Let me just like try and like convince myself that the left-hand sides of those two things are equal. The point is that it's a fin n f times card s, right? The set of evaluations, right? I think the point is that like fin.suck, what exactly does like go, how do I go to this? Like, am I, how do I go to definition? This is, I feel like in lane 3, okay, I feel like I literally just watched a video where Patrick Masso was like, yeah, you can like right click and go to it, but I am not like seeing a go to definition here. Is there something I need to like press? What is this? Reverse list, copy state to comment. Types, instances, yeah. Okay. We're just gonna go here. So fin.suck is a function from fin.n to fin.nsuck, which takes I to I plus 1. Okay, very simple. So this, then, is a function. What? Takes fin.n to fin.n. So fin.n suck, right? So this is, yeah, let me just, right, the inductive hypothesis has finset.card in it. And no fin.suck. So fin.suck, right? So just takes in a fin, right? This has only got n inputs, right? So there's only n inputs, and then I go through R. So there's n possible inputs to this. And there's now randomly pick R2, Rn from S by the induction hypothesis. The point is that for every, there's supposed to be like some sort of bijection between them, right? Okay, how do I like convert, right? It's convert IH. Yeah, we have to show that these are equal, and we have to show that those are equal. Well, we don't, okay, we don't precisely want to convert. What we want to do is we want to first show that like have this like yet another thing. We have that this is greater than or equal to the total degree of P sub I prime. Sorry. Okay, can I like done? That like stops processing at some point. Yeah, so I feel pretty confident in this fact. And then this is less than or equal to another, sorry. So if this is less than or equal to that, this is like another nat.mol. Exact. Like that. Then this, I convert wait, what is this? This is like convert IH. What exactly is the convert tactic? Convert is similar, but the type E is not required to exactly match the goal. Cool. And the point is that like this seems like something that is true for rather elementary reasons. Yeah, seems reasonable. Basically, the idea is that both of them like refer to the question of whether a particular evaluation of pi prime equals 0, and like in one case, it's like, yeah, I feel pretty confident in this. Sorry. Okay. So this moves on, like, yeah, like I'm putting aside these two sorries, which I feel pretty confident about. Let's like consider this third sorry, which I think is the one I feel the least confidence about. Although I'm not, I think it's probably right. This is the, okay, so this is the like yeah, this is the one I'm least confident about because I feel like here we're going all the way from A intersect B complement to I over S. And that's sort of a long way to go. What was the so what is the justification for this? The idea is that A intersect B complement, the probability of A and B complement is less than or equal to the probability of A given B complement. The probability of A given B complement is less than or equal to I over S. A given B complement. Problem is it's sort of tricky to the like conditional probabilities, right? The conditional probabilities like have to be like unfolded into like pairs of things or something. Right? If P sub I is not equal to 0, then P x1 R2 through Rn is of degree I, and thus not identically 0. Okay, is this like a second? Okay, this is going to blow my mind. Do we apply the induction hypothesis twice? I think, okay, no, I think this is not an this is just an application of the like univariate polynomials have at most degree many roots. That's all that's saying, right? Yeah, so if Pi R2 through Rn is non-zero, then P, yeah, so like considering like for like a fixed R2 through Rn, right? Like we can consider this polynomial P to be like a univariate polynomial. Given that R2 through Rn make Pi non-zero, Pi is just that, then P of x1 with all those values is not an identically zero polynomial, and thus has at least I roots. Yeah, okay. So this is going to require finding a lemma about that. Let's look for that lemma. It's like polynomial dot roots degree num roots, card roots. Yeah. Polynomial dot card roots. maybe yeah, so it's going to involve one of those two things. But like even before we can invoke that, we have to like understand how it's going to work with these sets instead of the probabilities. So I feel like the point is like, what are we trying to prove? What is less than what? We have, we are looking for the cardinality Yeah, it's very interesting how it sort of looks. The probabilities sort of argument breaks down. So the cardinality of the set of functions where p evaluates to 0. So like R, for example, is that. Let's filter. The filter is over like, that's again tough, yeah. So where p equals 0 and pi prime is non-zero, is at most I times finset card Sn. And I think the point, yeah, so is the way that we want to approach this like this? Like, I think the idea is like for any, like we first choose the s to the n, right? We choose the like, we choose the successors, right? And we say that, okay, for any choice of successors, yeah, okay, this doesn't actually seem like it's going to be as hard as I thought it was going to be. For any choice of like R2 through Rn, you know, either it's going to be that like this is equal to 0. Sorry, wait, let me clarify my mind. Either it's going to, like for any choice of R2 through Rn plus 1, it's going to either be the case that this is equal to 0, in which case none of it doesn't count, right? Or it's going to be the case that this is not equal to 0, in which case it counts, but we can only get like, there are only like I more choices for the first value that will make this work. And so like for each of the finset.card s to the n choices for the like the successor values, it's going to like we're going to be like assured that like this they'll like that set only contributes at most I to like this total. Okay. Right. What is like striking me now is the idea that like before I move forward, like I feel like I'm definitely going to have to like unfold the definition of function finset though. And that's a problem because function finset is not in MATLAB. It is just a like random thing that I'm trying to define. And so I feel like I need to go and either like convince the MATLAB maintainers to put that in there, or like figure out how I'm supposed to be doing it. Okay, well, that seems like a good as place as any to stop for the night. Good evening.